All right, so this week we're going to be talking about different types of statements, and we're still going to be using our truth tables in order to determine what types of statements certain WIFs are. So the first type of statement is a contingent statement, and this is a statement that is sometimes true and sometimes false. And a good example of this is P or Q. Now, the truth value of this entire statement depends on its component parts, but if we look under the main operator of this OR statement, what ends up happening is, I believe it's TTTF, because in the first row, P is true, Q is true, so that disjunction as a whole is true. In the second row, P is true, Q is false. We got one true disjunct, so the disjunction as a whole is true. In the third row, P is going to be false, but Q is going to be true, so the disjunction as a whole is true. But in that last row, P is false, Q is false, so the disjunction as a whole is false. So under the main operator of a truth table, we have TTTF. And since sometimes it's true, sometimes it's false, even though it's only false once, this is still going to be considered a contingent statement. Now, a non-contingent statement is the opposite, where it's not sometimes true and sometimes false. It's either always true or always false. So the truth value of the main operator does not depend on its component parts. When we're looking at the truth table, these statements are either always true and always false. We have these two kinds. A tautology is going to be always true, and a self-contradiction is going to be always false. So a tautology is a statement that is necessarily true. So under the main operator, it's always true. So one example here is P or not P, and this is true whether or not P is true or false. So let's look at this. So P is true. So in this case, we got a T over here, and then not P is going to be false. And this row down here, if P is false, well then P is going to be false, but not P is going to be true. Now if we're looking at the main operator, which is this OR, so long as one disjunct is true, the disjunction as a whole is true, and in this case, so long as one disjunct is true, the disjunction as a whole is true. So underneath the main operator, we have all T's, which makes this a true, true always, necessarily true, the tautology. A self-contradiction is a statement that is necessarily false. So one example is P and not P. So we'll fill out this truth table to show you guys. If P is true, then P is going to be true over here, but not P is going to be false. If P is false down there, P is going to be false, but not P is going to be true. Excuse me. Now we look at our conjunction, and for a conjunction to be true, both conjuncts have to be true. In this case, we have one false conjunct here, so this is going to be false. Down here, we have one false conjunct down here, so this is going to be false. So the row or the column underneath the main operator is always false, and that's a self-contradiction. So when we're looking at one compound statement, we can say, we can evaluate it as being contingent or non-contingent, and if it's non-contingent, we can say whether it's a tautology or a self-contradiction. But sometimes we want to talk about the relationship between two compound statements. And one such relationship is that of logical equivalence. So logical equivalence is when two truth functional statements that have identical truth tables under the main operator. That means that everything under the main operator they're identical in each row. And so I've already done this one for you. P triple bar Q is logically equivalent to if P then Q and if Q then P. But let's go through it one more time just to be sure. So for a biconditional to be true, both P and Q have to be true, or both P and Q are false. But in these other rows, where P is true and Q is false, or P is false and Q is true, the biconditional is going to be false. Now, if we're looking at the opposite side, if P then Q, that's going to be true, false, true, true. So, because it's only false when we have a true antecedent and a false consequent. And then if we're going to the other side, it's going to be true, true, false, true. Because again, it's only false when we have a true antecedent and a false consequent. And now we're looking at the conjunction, and conjunction is true when both conjuncts are true. So it's true in this row, false in this row, false in this row, and true in this row. Now notice, look, we have TFFT under our main operator of the biconditional, and under the main operator of the conjunction, we have TFFT. So they are identical. In this row it's T, in that row it's T. In this row it's F, in that row it's F. In that row it's F, in that row it's F. In that row it's T, and in that row it's T. So they are identical, which means that we can say that P triple bar Q is logically equivalent with if P then Q and if Q then P. Here's another example, one that we haven't covered yet. So I already set up this left-hand side, but let's work through these two compound statements. So the first one, what's the main operator? Well, the main operator is the one outside of the parentheses, which is this negation right here. So first, let's find the values of this disjunction. So TT is going to be T, TF is going to be T, FT is going to be T, and FF is going to be F. Because remember, disjunction's true so long as at least one disjunct is true. But now we need to look at the main operator, which is this negation. So if it's T down there, over here, it's going to be F, 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 T. All right, this one is a conjunction. Both of the conjuncts are negations. So I'm going to fill out those negations just so that I'm playing it safe. We end up with F, F, T, T over here. Then on this side, we have F, T, F, T. Because remember, it's going to be the opposite. If C is true, not C is going to be false. Now we look at the main operator, the conjunction. For conjunction to be true, both conjuncts have to be true. So we get F, 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 T. Now, if we're trying to say, is this logically equivalent? We look under the main operator. We see we have F, 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 T. We look under the main operator. We see we have F, 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 T. They are identical. So these two statements are logically equivalent. Not the case F or C is logically equivalent with not F and not C. So along with logical equivalence, we also have another relationship between two compound statements, and that is of contradictory statements. So two statements that have opposite truth values under the main operator on every line of their respective truth tables. So let's look at this example here. We have not F or S, and then we have F and not S. So let's go with this one first. Which one's the main operator? The or, because that negation scope is only on that F. So if F is true, then not F is going to be false, false, true, true. And then S stays the same. So I'm not even going to really worry about that. Here's where I will put the main operator, the or. So we have a false, not F, but we have a true S. So it's going to be true, both false, not F, and a false S. So that's going to be F. We have a true, not F, so I already know it's going to be true. I don't even have to look at S, but it is true, so it doesn't matter. Then we have a true, not F, so I know it's going to be true, even though we have a false S over there. So this is the main operator, the one that I'm looking at. Over here, I already have the F, so I'm going to leave that there, but I'm going to write down the not S's, so I'm safe. That ends up being that. Why? If S is true, not S is going to be false. If S is false, then not S is going to be true. So now I'm looking at this along with this, and it's a conjunction. So both have to be true in order for the conjunction as a whole to be true. Since this is an F, I know it's going to be an F. And this is a T. I look over here, it's a T, so I edit T. This is an F, so I know it's going to be an F. I don't even have to look over at my F. And this is a T, but that's not enough. I got to go look. Oh, but that's an F, so we get an F. And now we're saying, all right, is this a contradictory statement? I look at the main truth values here. I look at the main truth values here, and I see if are they opposites on every single row. Here's a T, that's an F. Here's an F, that's a T. Here's a T, that's an F. And here's a T, that's an F. So yes, in every row, they have opposite truth values, which means that these are contradictory statements. And then we also have consistent statements. And consistent statements mean that at least one line on their respective truth tables where both main operators are true at the same time. So we're just looking for one single row where both main operators are true at the same time. So let's go through this example. R or B, we got T, 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 F. And then we have R or not B. So I'm going to do the not B first. So if it's true over here, it's false, false, true, true, false, false, true. And now I got to look at this row and compare it with this row to get my main operator. So not B is false, but R over here is true. Not B is true, so that's true. They're both false, so that's false. And it's true over here, so it's true there. So for this one, I'm looking at this row or column, and I'm looking at this column. And now I got to look at the rows and see, are there any rows where both main operators are true at the same time? And yes, we have this one row right here where they're both true. So I don't even have to look at any of the other rows. I know from that one row that these two statements are consistent. So let's imagine though, like that this was false. Yeah, that's the only one I need to change. This statement is still going to be consistent because you just need one row. It doesn't matter that these aren't consistent. Doesn't matter that these aren't consistent. Doesn't matter that these aren't consistent. The only thing that matters is that these are consistent. So this statement or these two statements are going to be consistent statements. They have at least one row where both statements are true. Doesn't matter if all the other ones are not, or different values, or they're both false. Doesn't matter. You just need one row. All right, inconsistent statements. So these are statements that when we're looking at the two compound statements, there's not even one line in their respective truth tables or their main operators are both true. They both can be false at the same time, but there's not a single line where they're both true. So this is the difference between inconsistent and contradictory. For contradictory statements, they always have to have opposite truth values. For inconsistent statements, if both of the truth values are false, then they're not going to be contradictory, right? Because for contradictory, if one's false, the other one has to be true. If they're both false, then they're going to be inconsistent. So let's go through this. I already got my C's there, so I'm going to do my M's. And then I'm going to evaluate this row, this column with this column, and it's a conjunction. So it's false there, true, false, false. Because if it's false at all, it's going to be false. In this case, it's false over here. Now I got C triple bar M, so it's going to be T, F, F, T. And now I'm looking at this column and this column. And I look, all right, so I got an F and a T. So those are, what I'm looking for is there even one row where both are true? Is there even one row where both are false? Here's an F and a T, so that's not both true, but it's not both false. So we still haven't eliminated the possibility that this might be a set of contradictory statements. Look at the second row, got a T and an F, so they're opposite, so haven't gotten any proof that this is a consistent statement, but still haven't gotten any proof that it's inconsistent versus contradictory. Could still be contradictory. But then I look at this third row, I got an F and an F. So this eliminates the possibility that these statements are contradictory. And it's giving us some reason to think that these two statements are inconsistent. But I have to look at every single row, because if there's at least one row where both are true, then these statements aren't inconsistent, they're consistent. So I look at the last row, I have a false over here and a true over here. So there's not a single row where both are true. And it's not the case that they have different truth values under each under each row. Why? Because we have this third row where they're both false. So we can say that these two statements are inconsistent, they're not contradictory, and they're not consistent. So that's it for this week. I know it's spring break, so there's spring break coming up next week. So I'm hoping that you guys watch this within the next couple of days and get this work done so that you can enjoy your spring break and you don't have to worry about logic. All right. Have a wonderful spring break, and I will see you next week.